Okay, great. We're ready to go then.
Okay, thanks. So, we're going to start. So, hello everyone. I'm presenting this paper that we presented in VTC 4 2016, titled Performance Analysis of Beam Sweeping in Millimeter Wave Assuming Noise and Imperfect Antenna Patterns. This is joint work with my supervisor, Dr. Robert Heath. One of the motivations for millimeter wave is to try to use the huge amount of data rates, huge amounts of bandwidth that is available to provide high data rate applications. So, as an illustration of how large the bandwidth are at millimeter wave, I show here the bandwidth used for the 802.11 standard family. And here, for example, if we assume that the 802.11n has a bandwidth of 1, then the newer version of the Wi-Fi standard called 802.11ac uses 4 times that. And the 802.11ad, which is Wi-Fi at 60 gigahertz bandwidth, 60 gigahertz carrier frequencies, have 54 times that amount of bandwidth. So, however, this bandwidth is not that, it does come with challenges. So, one of the challenges that is the shrinking antenna apertures due to the increase in the frequencies. So, as an illustration, that at low frequency you have a larger aperture, and with millimeter wave you have a smaller aperture. And to compensate for that, we need to use an antenna arrays. And to do that, by using antenna arrays, meaning that we will focus the energy at certain directions, and this directionality, the implication of this directionality is that you have to point at the right, at the position that is the receiver is listening to, otherwise we cannot get a signal. So that means beam alignment, accurate beam alignment is very important in enabling high data millimeter wave communications. So one of the most practical approach in doing beam alignment is what is called the beam sweeping. And what it does here is illustrated by this figure here, that this station 1 try to find the best direction to transmit to this station number 2 here. And one easy way to do that is to just sweep, that is, try all the different beams here. That is this sector 1, 2, 3 here. And the other side just use a quasi-omni pattern to listen and then just feedback which one was the best. So many of these beam sweeping based approach, they try to use this kind of a wide beams that is called quasi-omni here in the initial stages. And the reason for that is to try to make the search efficiency, to increase the search efficiencies. However, when we use the wide beams, there are problems with, there's 2 main problems. One is that when we use the wide beams, we don't have the antenna gains. That means we have low SNR during the beam training, and that could lead to error beam selection. And another reason have been reported in this reference that I cited here, is that when we try to realize wide beams, the antenna gain is not flat. It has some fluctuations, meaning that at certain direction the gain is higher than it should be, and at certain direction the gain is smaller. And this can also cause some. This can also result in beam measurement errors, because it might de-amplify a certain good link because of these fluctuations. So, in this work, we try to capture these 2 effects to try to understand the impact of these 2 effects on the beam sweeping performance. So there's a number of related work in this area, and actually there's a lot I could not include here, just include a few main work that did that work in this area. One is so there's a number of proposal of this different beam alignment method based on beam sweeping, and I show here two two approach here. One is kind of a tree-based approach. That means we search it by level, and they have these different levels of codebook and try to search it with different resolutions. And another approach is a more sophisticated one, what is called the adaptive bit subspace sampling. And there's also some analysis of the impact of noise and the antenna fluctuations. However, for example, the work in 2, they did quantify some of the impact of noise, but there is no antenna gains fluctuation included. And another work in 3, they use they quantify the gain fluctuations, but there is no noise in the analysis. And our analysis, we include both effects, and we also introduce what I call the power loss. That means we try to capture the misalignment severity. That means if we choose a suboptimal beam that is 1 dB different from the optimal one, or it is 10 dB different from the optimal one, it has a huge difference. But the work, for example, in 2 that they call the misalignment does not differentiate between their two cases. So start with our model for this analysis. We assume kind of this model here, the received signal power. GI is the received signal power, and we have this PI here is kind of the power of the path when we use a certain beam pair here. For example, here when we use this beam number 1 here, we have this path gain of P1, and this P1 includes the transmit power, and if we use kind of a spreading codes, the spreading gain will also be included in this parameter P. And the gains of the transmitter side is by this XT, and the gain at the receiver is XR. And the gain fluctuation, what I mean by gain fluctuation is illustrated here. For example, at this point at XR1 here, it is boost because of this gain fluctuation. The gain here is higher than the actual gains of the antenna because of the imperfections of the antenna pattern. And we assume an additive noise power here, VI, which is one last point I want to make is that this model here, as I said, we include the spreading gain in this PI, so it is applicable to both narrowband and wideband channels. So the next is the model for the quasi-omni pattern gain fluctuations, and this model is based on the work I cited here. They have did some electromagnetics simulations of the realization of the antenna arrays, and as shown here, there's gain fluctuation that is, as you can observe here, which can be very high. Which can be very high at certain cases. It can be a dip. It can boost more than the average antenna gain that you should expect from an ideal antenna arrays. And from these simulations they have derived an empirical model, and they have shown that it fits well with the Laplacian model, Laplacian distributions, and this is what we used here. And some of the main parameters here, there are two main parameters here. One is the average antenna gains, and another one is this phi here represent the fluctuation level. And that will be explained, well, the adapted number will be given at when we provide a numerical example. So I will consider two beam alignment method in this analysis. One is called the sector level sweep, that is SLS method. This is the method used in 802.11ad, and another one is used in 802.15.3c, and short for 3c method here. And they do pretty much similar thing, but the SLS method use what is called a single-sided search, meaning that one side use the quasi-omni and the other side use the narrow beams to search all the different directions. And the 15.3c method, they have this different levels of codebook, and they do exhaustive search at different levels of the codebook. For example, at the quasi-omni level, they have, for example, here the transmitter have 2 quasi-omni patterns, and the receiver have also 2 quasi-omni patterns. They just try all different combinations. And one point that I should point out is that SLS method can suffer gain fluctuation only on one side because it uses the quasi-omni at only one side, and the 15.3c method uses it at both sides. So that means the gain fluctuation is more is double for this for the 3c method. And for our analysis, we consider only the part that involve the quasi-omni pattern, because when we use a narrow beam at the sector level, usually the gain fluctuation is not a big deal. So to introduce the severity of the beam alignment, the beam misalignment, we introduce this kind of a model, the channel model here, for the different receive power when the different beam pairs are used. For simplicity here, you just sorted the receive power in terms of index order, like here. The first index is the best one, it has the highest receive power, and I define this data P, which is kind of the gap to this the best path. And I defined the power loss of as this, as shown here. That is, if after the beam training, for example, the I's best beam pair is chosen, we say that there is the power loss of data P of I. And by this definition, data P of 1 is 0, maybe. And with that, we can compute the power loss probabilities by this from that definition of the power loss. Is that the probability that the beam measurements of the I beam pair is larger than the rest of the beams. And this is a sketch of the derivations of this of the probabilities of misalignment here. One main assumption that we use here is that the gain fluctuations experienced by all the different beams are independent. So the rationale for that is because the AOA and AOD of each path are independent, and so the gains of each path should be independent. And so this will lead to the GI, which is the receive power of the I beam pair, will also be independent. And with that, we have this expression here, and if we condition this on this GI, these different events will be independent, and with that we can simplify it into this product of the probability of different probabilities of these different events. And after that, we can just average out this conditioning GI to get this expression, and that will give us the final power loss probability. And this is the simulation setting that I will show in the next slide, the numerical results. So I consider 2 types of channels. One is line of sight channels, and another is a non-line of sight channel. So the difference here is the gap from the optimal beam pairs to the second best beams. So the line of sight channel tend to have a larger gap, and here is assumed to be 10, and the non-line of sight channel have a smaller gap, and here assumed to be 3. And the SNR after alignment is set to 5, 15, and 20 dB. And for the gain fluctuation, the parameter for the gain fluctuation for the Laplacian distribution, the Laplacian distribution is shown here for the SLS method and 3C method. One assumption here is that to make the overheads relatively similar, we need to use a narrower quasi-omni beams for the 3C method, and that is why the mean of the antenna is higher than that of the quasi-omni used in the SLS method, and the fluctuation is lower. And the final sector level are the same for both cases. We have the beam width of around 15 degree and a gain of around 13.8 dB. And this is the result for the SLS method. We assume by that assumption we have 8 different beams, 8 different sectors. So we can have different levels of power loss based on that which pair is selected. So for the line of sight channel here, we can see that when the SNR is high enough, it's get very quite accurate, more than around 90%. And when the SNR is very low, then it cannot differentiate between these different beam pair because the gain is lower than the noise level, so that the beam measurement does not help. It cannot differentiate the different beam pairs, and so any beams can almost equally likely selected. And when we move to the non-line of sight channel, we can see that there is a large drop at this point here for the beam, for the aligned case. And this is because of the lower gap to the second base beams, so that it's easier that the noise level can flip it. And one other point that I should make is that when we increase the antenna high, when we have a high antennas, the fluctuations of the antenna become problematic for this non-line of sight channel. And we have a similar trend for the 3C method. The only difference is that we have a smaller gain fluctuation, so that the trend that we see in the SLS method is kind of amplified. For example, in the line of sight channel, we get a very close to 1. The probability of aligned is very close to 1. And also here we have a higher probability of being aligned because the gain fluctuation is smaller. So some of the implications that we can obtain from this study is that for the line of sight channel, it's more limited by the noise, by the measurement noise, and in the non-line of sight case, it is more limited by the antenna gain fluctuations. So what it means is that if we are in a use case scenario like wireless backhaul, meaning that we are likely to have line of sight, then we should have enough gains by either use a higher transmit power or use a larger spreading gains to have enough receive signal during the beam training. But even in the non-line of sight case, it's also important. For example, in the use case of Wi-Fi or in the cellular, that we could have non-line of sight, then the gain fluctuation can also be a problem. So that has to be taken into account. And so one other thing for future work, it could be that if we can include the positions of the user, then we might be able to adapt the spreading gain or transmit power to have a good beam alignment accuracy while not wasting too much resources on the beam training. So as a conclusions, to summarize, we have derived power loss probabilities that capture both the measurement error, the noise measurement error due to noise, and the gain fluctuations of the antennas. And some of the conclusions, some of the implications that we can draw is that line of sight dominant path use cases can have a low requirement on the antenna gains, but for non-line of sight cases, we need a more accurate, a more flat antenna gains.